SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about some advanced RANS models. Now, to start with, let us discuss about special features of near wall flows. Across a turbulent boundary layer, the flow has to undergo a transition from fully developed turbulent flow to completely laminar within the thin viscosity dominant sublayer adjacent to the solid surface, which means if we travel across the fully turbulent core region at the edge of boundary layer to the wall, the phenomenon is termed as low Reynolds number turbulence, and the transition from high to low Reynolds number regions is determined by local turbulence Reynolds number RT given by rho k square by mu into epsilon. This can be interpreted as rho into k to the power half. K to the power half is equivalent to velocity into k to the power 3 by 2 divided by epsilon. So k to the power 3 by 2 divided by epsilon, that is the turbulent length scale, divided by mu. So rho into k square divided by mu into epsilon can be interpreted as rho into k power half into k power 3 by 2 divided by epsilon into 1 by mu, which is basically turbulence Reynolds number, where k is the turbulence kinetic energy and epsilon is the dissipation. Epsilon is the dissipation of turbulent kinetic energy. The significant physical effect of the presence of a wall is the viscous diffusion terms, which are usually negligible compared to other terms in the regions away from the wall, become one of the largest terms to be balanced by other terms. Now, usually structure of turbulent boundary layer can be thought of three zones, comprising of three zones. One is viscous sublayer, which is within y plus equal to 12, 0 to y plus equal to 12. You may recall y plus is a length scale given by y u tau by nu, and u tau is the friction velocity. So within the viscous sublayer, we have linear relationship between U plus and Y plus. Again, Y is Y into U tau by nu. The log layer, which is between Y plus equal to 30 up to some distance, which is function of Reynolds number, where the inertial terms can still be neglected due to vicinity of the wall, but the viscous stress is also negligible. Viscous stress, because this is outside the viscous sublayer, that is also negligible. So here the Reynolds shear stress term or Reynolds shear stresses are significant. And then the defect layer, where the flow becomes like far wake behind a non-streamlined body. So roughly this is the structure of turbulent boundary layer. And when we use wall function approach, what we usually do, we assume the laminar sublayer and we take the first computational point at the edge of laminar sublayer. Let this point be P, and at this point the turbulent kinetic energy, we do not use the turbulent kinetic energy equation, we use the turbulent kinetic energy equation within the field, but the first point P, it is directly prescribed as boundary condition, and that is given by U tau square divided by C mu to the power half. Similarly, epsilon is given by epsilon P equal to U tau cube divided by kappa into Yp. Yp is the normal distance from the wall. And in K omega method, omega P is K power half divided by C mu power 1/4 kappa Yp, where C mu is the closure coefficient we have already discussed, and U tau I have already mentioned, friction velocity. This is basically wall shear stress divided by rho, entire quantity is under root. Now when you compute, actually this quantity U tau is not known a priori, because we use log law within the fully turbulent region. It's a basically log law profile, something like universal velocity profile, and commensurate with the kinetic energy and epsilon in the field. And then we assume that at the edge of boundary layer, whatever is the shear stress laminar sublayer, that is directly transmitted to the wall. And from there we calculate that means tau turbulent is equal to tau W, and if we know tau W, from there we calculate U tau. From U tau we again calculate Kp, and that Kp comes as boundary condition. In the field again we compute for K kinetic energy and epsilon through the differential equation, and then we compute the turbulent viscosity, compute the full Navier-Stokes equations, and find out the turbulent velocity profile, again calculate its value at the edge of sublayer, thereby we again calculate turbulent shear stress, and that is again equal to the wall shear stress. From there again we calculate U tau. This new U tau square by C mu power half becomes the boundary condition. K kinetic value of kinetic energy, turbulent kinetic energy at point P, that means at the near wall point. So these are all boundary conditions. Again we solve. So basically this is outcome of iterative type of solution algorithm. And kappa, which is there in the expression of epsilon p and omega p, the kappa is von Karman constant. Usually value of 0.4 is taken. For some special separated flows 0.39, 0.38, such values work. As such, according to one of the experts in turbulence and turbulent flow field, Professor Franz Durst, he thinks that this value should be 1 by E, which is close to 0.38. Now, as I mentioned, that some researchers prescribe low Reynolds number version of K epsilon model, low Reynolds number version, and that means near the wall low Reynolds number version is used, and away means little away from the near wall region, that means in the core region, again high Reynolds number, usual K epsilon equations are computed, and they derived, I'm not going into derivation details, the low Reynolds number K equation and low Reynolds number epsilon equation. So basically this equation is given by, as we can see, that del T of rho into K, then convective term, and right hand side we have diffusion term, production term, dissipation term, and other terms d and pi. Similarly, del T of rho epsilon tilde, this epsilon tilde is basically epsilon for away from the wall, and the near wall region epsilon value is epsilon. So the epsilon and epsilon tilde, they are related by this relationship, rho into epsilon equal to rho epsilon tilde plus d, where d is a constant and p is the production term, kinetic energy production, and mu t is the eddy viscosity or turbulent viscosity. It is given by rho C mu F mu K square by epsilon. So instead of C mu K square by epsilon, or if rho is consumed, that is nu t, instead of C mu K square by epsilon, it is C mu into F mu K square by epsilon. If you transfer rho to the left hand side, this will be nu t. Nu t is C mu K square into F mu by epsilon, whereas usual nu t is C mu K square by epsilon. This F mu is basically a damping coefficient. Similarly, there are few other coefficients, F1, F2, D, pi, and E. Now, Usually in K epsilon model we have seen some model constants we have used. C mu 0.09, C1 1.44, C2 1.92, sigma K 1.0 and sigma epsilon 1.3. These we have discussed in quite rigorously, we have discussed in our earlier lectures. Now, standard K epsilon model, which was developed by Professor Spalding and Professor Launder, that was modified by several researchers. One among these groups is Jones and Launder, another is Launder and Sharma, another researcher is Chien. This model is very popular. Another group of researchers are Lamb and Bremhost in Australia, Shi and Mansour, again in Stanford University, and Nagano and Hishida in Japan. So they are identified by the acronyms JL, LS, CH, LB, SM, NH, and different C mu, C1, C2, then sigma K and sigma epsilon, they have used to validate their models or their proposals. Now this damping coefficient we have introduced here, d pi, f1, f2, f mu, e, these are, we have tabulated, these have been used by all these researchers I mentioned, and these are different values they have used. You can see standard f1, f2 are not there, is equal to 1, f mu is also 1. If you substitute all these values as 1, it will get into standard K epsilon. But then, Jones Launder, Launder Sharma, Chien, Lamb Bremhost, Shi Mansour, this is basically last one is Nagano and Hishida. So they have used all these expressions, and in these expressions you will see that turbulence Reynolds number RT, which I have already discussed, rho K square by mu into epsilon, and RK, which is rho K power half y by mu, and y plus, of course we know that is y into u tau by nu, or rho u tau y by mu. These values have been used. Similarly, pi, d and e, these values also standard Jones Launder, Launder Sharma, Chien, Lamb Bremhost, Shi Mansour, Nagano and Hishida. It's not that all the parameters have been used by everybody. That is why you can see quite a few parameters are 0 for Jones Launder, Launder Sharma, etc. And D and E, their values have been used. And it is like, some worldwide workshop, different groups at different locations, they were experimenting with different models and, trying to compare complex flows and compare their results also. So, these models are all very exciting. One can look into them, and they have extensive comparison with the database of Coles, and I have discussed already about that in the earlier K epsilon related lectures. Now I will mention about two very special models. One of them is RNG K epsilon model. RNG means renormalized group K epsilon model. You might be knowing renormalized group theory is a very well-known theory in statistical physics, and famous researchers Victor Yakut and Steven Sorsag, they are in Princeton University. So they wanted to generalize RNG theory for turbulence modeling. And you can see from this graph, we can observe that solid band indicates the small length scale eddies that are removed from the dynamics, and then increase of viscosity from new molecular to new effective, basically that decrease the effective Reynolds number. Now, what is done? See, as I told you, turbulence is composed of several length scales. Now, these length scales can be thought about different oscillations. Each oscillation or each oscillatory wave, one can think about its wavelength, its time period, and frequency. Now, time period is large, means frequency is less. These are large scale eddies. Time period is small, means these are high frequencies. Usually these are like fully developed turbulent flow are dominated by high frequencies. That means small scale eddies. More the small scale eddies are present, the character of turbulence or the velocity becomes more universal. Velocities become unpredictable if large scale eddies, that means low frequency oscillations, are present. They want to show each low frequency oscillation wants to show its character. It deviates significantly from flow to flow. But when the flow is dominated by high frequency oscillations, small scale eddies, they become more general. Now, what Professor Victor Yakut and Stephen Sorsag, they did, they basically tried to combine the effect of low frequency oscillations, that means large scale wave numbers. They wanted to merge their effect with the small scale or the high frequency small scale turbulence and small scale oscillations, and tried to develop a model which can be valid for a wider class of flows. The RNG method is applicable to scale invariant phenomena lacking externally imposed length and time scales. For turbulence, this signifies that the method can describe the small scales which should be statistically independent of the external initial conditions and dynamical forces that create them through different instability phenomena. So basically, the large scale oscillations or low frequency, large time period, low frequency oscillations, they become source of perturbation, disturbances. They produce unstable condition. They are the sources of instability. And finally, maybe different routes. Sometimes it is period doubling route, sometimes it is quasi-periodic route. The small eddies are created. And RNG method gives a theory of Kolmogorov equilibrium range of turbulence, where the energy becomes basically a function of k power minus 5 by 3, similar such slope. So that means this is called inertial subrange, and usually this range dominates in a fully developed turbulent flow field. So when this RNG K epsilon method was developed, around the same time Professor Launder and his student M. Kato, they developed also a theory which is almost similar to RNG K epsilon. This is called Kato-Launder K epsilon, Kala K epsilon. And what we have done here, we have tried to use a general expression so that the expression is valid for standard K epsilon, it is valid for RNG K epsilon, also it is valid for Kato-Launder K epsilon. So this is the K equation. We have already been introduced. Temporal term, convective term. See, convective term, we have used uppercase ui as a velocity, and when we first discussed, we used u bar I. Now u bar I or u uppercase I, they are same. Mean velocity in I equal to 1, 2, 3 or x, y, z, 3 directions. And this is the production term, this is the basically diffusion term, and this is the dissipation term. And then epsilon equation, similar way, this is a convective term, this is a convective velocity, and the way we wrote epsilon equation, exactly same way it has been written, but you can see some additional terms like R. And also this pk is a production term, and that means turbulence generation term. It is for RNG, pk is c mu into epsilon into s square of s. S is given by k by epsilon root over half del ui del x j plus del uj del xi squared. This is basically shear rate deformation type of term, and you can see this has been multiplied by K divided by epsilon, half del Uy del Xj plus del Uj del Xi, I equal to 1, 2, 3, j equal to 1, 2, 3. If you substitute for each I, that means each I equal to 1, j will be 1, 2, 3. Each I equal to 2, again j will be 1, 2, 3. I equal to 3, j will be 1, 2, 3. You get the full term. That is basically the production term. And that is there in RNG model. But in Cato-Launder model, pk means c mu into epsilon. Instead of square of s, they have used s into uppercase omega. And what is uppercase omega? Uppercase omega is k by epsilon root over half del uy del xj minus del uj del xi. This is kind of rotation type of term. So this uppercase omega into s, instead of square of s in RNG, in Cato-Launder it is uppercase omega into s. And effect of average rotation, as I said, of the fluid elements is brought about by this capital or uppercase omega term. And RNG has another additional term, R, which is c mu eta cube into 1 minus eta by eta naught into epsilon square divided by 1 plus beta naught eta cube into A, where eta is given by, again you can see, k by epsilon into del uy by del xj plus del uj by del xi into del ui by del xj, expansion for each I equal to 1, if you vary j equal to 1 to 3, I equal to 2, j equal to 1 to 3, I equal to 3, j equal to 1 to 3, it will be producing some dissipation expression equivalent to dissipation. So multiplied by k, having found the square root of that term, then multiplying by k and dividing by epsilon, we get eta, and then we plug in that eta in this R term to create the R term. For Cato-Launder model, there is no R. We have written in a generalized way, there will be no R for Cato-Launder model. And for RNG k epsilon, c mu, c epsilon 1, c epsilon 2, sigma k, these terms are little different. This is not 0.9 c mu, this is, say, we have so far taken c mu equal to 0.09, but here c mu equal to basically 0.845, c epsilon 1 1.42, c epsilon 2 1.68, and sigma k 0.7179. Now the effect of swirl, that means rotation, on turbulence is included in the RNG model, enhancing accuracy of swirl flows. If the flow is basically swirl dominated, rotational spiraling component is there, then it becomes a complex flow, especially with respect to generation and dissipation of turbulence. So RNG takes care of such situations very effectively. The RNG theory provides an analytical formula for turbulent Prandtl number, and RNG theory provides an analytically derived differential formula for effective viscosity that takes into account low Reynolds number effects. Now here we have computed, these computations were done in IIT Kanpur by Professor A.K. Saha. So this is, of course, long back. It's a paper by Saha, Biswas and Muralidhar. We have given comparison of this is the same computation flow past a square cylinder in a confined channel, standard K epsilon, Cato-Launder K epsilon and RNG K epsilon. Here because of paucity of time, I cannot compare or give you the difference and comparison of the vertical structures that were derived, but all three methods worked well. For blob body flows, blob body means square cylinder, circular cylinder, which are non-streamlined bodies. For blob body flows, a comparison between the computations and experiments were made for the time averaged kinetic energy variation along the center line in the downstream of the blob body. We have seen that in this picture. Cato-Launder model predicted the peak value of turbulent kinetic energy in good agreement with the experiment. As such, when we did this computation, we compared the computation with the experiments of another very well-known, internationally well-known group of Professor Wolfgang Rodi in Germany, and Professor Rodi and Dr. Lin. They did the experiments and we compared with their experiments. That is why we have written kinetic energy, turbulent kinetic energy, peak value of that computed by us was in good agreement with the experiments. The peak value of turbulent kinetic energy due to RNG K epsilon model showed some departure from experimental values. Although RNG K epsilon is in general very superior model, but in this case its performance with respect to few parameters were little inferior to Cato-Launder model. And Reynolds number of interest that we used or experiments of Lin and Rodi, that was you can see 21,400. There is another model which is also very popular. This is again K epsilon but modified K, modified epsilon. You can see this production term and PB, these two terms are extra terms in K equation. Similarly, epsilon equation also having PK and PB, these terms. S is a scalar value of the strain tensor. Just like what we have seen earlier, S is similar. Turbulent viscosity nu T is calculated but in that calculation, that means C mu K square by epsilon, C mu is no longer a constant. Its value is given by 1 divided by A naught plus AS U plus K by epsilon. where A naught is 4.04, AS and U plus are functions of both the mean strain and rotation rates. The angular velocity of the system rotation and the turbulence field, these are functions of that. So this is another popular model or another significant development on K epsilon model. That is why I have mentioned. Now I will briefly mention, I will not work it out, about the Reynolds stress model. So that means you don't express Reynolds stress in terms of mean velocities and a coefficient. Coefficient, what we have done so far, Reynolds stress, we have expressed in terms of mean velocity gradient multiplied by a coefficient which is known as eddy viscosity or turbulent viscosity, and then that turbulent viscosity is a function of K, function of epsilon. Then we are computing K, computing epsilon, finding out turbulent viscosity, turbulent viscosity into mean velocity gradients. Those we are substituting in basically Navier-Stokes equations and calculating the velocity field. But there is a method where the Reynolds stress term is directly calculated, and this is very general form. I will reduce it little more known form. Ui prime into uj prime we have discussed already several times. This is the Reynolds stress. So temporal derivative of Reynolds stress plus uk into del xk of ui prime into uj prime over bar. This is convection of Reynolds stress, del t of ui prime into uj prime over bar. This is temporal derivative of Reynolds stress. This is convective derivative of Reynolds stress. This term is called diffusion, and here you can see also triple correlation. Then you can see viscous diffusion of Reynolds stress, production of Reynolds stress. This is called pressure strain term, and this is dissipation term. And this is the term due to rotation, and this is the term due to body force. This is expansion coefficient, this is gravitation, this is the body force related. This is the external force, and this is also rotational force because of imposed rotation. So these two terms are additional terms. Otherwise, temporal derivative and convective derivative are related to diffusion, viscous diffusion, production of Reynolds stress, diffusion of Reynolds stress, viscous diffusion of Reynolds stress, production of Reynolds stress, pressure strain correlation, and dissipation. Now you can see it's a really extremely complex calculation, and the significant development of Reynolds stress models were done by Launder. This is a GFM paper 95, then 1975, sorry. This is Launder et al. 1975, Gibson and Launder 1970, Launder et al. 1975, Gibson and Launder 1978, and Launder 1989. These papers are landmark papers for Reynolds stress models. Now, Reynolds stress models are robust, capable of capturing nuances of turbulence statistics in complex flows, flows with rotation, flows with severe body forces, that means buoyancy driven forces, and all such complex situations. But as I said, it's extremely involved, and computational budget, computational effort is huge. It is these days, you must have heard that we use DNS, direct numerical simulation of turbulence, or LES, large eddy simulation of turbulence, which we'll take up in due course. Those are quite involved and, quite accurate, whereas Reynolds stress model is accurate definitely, but its involvement, its budget, computational effort is huge, even comparable to LES and DNS. And before emergence of LES and DNS, this was attempted, became popular, became effective tool, but very few groups got success. The groups which got phenomenal success with the Reynolds stress model are led by, one is of course Professor Brian Launder. He was in UMIST, University of Manchester Institute of Science and Technology, is widely respected world over as a turbulence scientist. Then another is Professor Mike Leschiner. He is now in Imperial College, London. Mike Leschiner also got phenomenal success with Reynolds stress model. And another is Professor RMC So in Hong Kong. Earlier he was in Arizona State University, now he is in Hong Kong. He also was very successful. But as I said, that usually turbulence research today is centered around LES and DNS and several variants of LES and DNS. Although Reynolds stress model is attractive, but because of complexity or whatever maybe other reason, it is not so popular today. But it's a very involved and rigorous method and scientifically very accurate. So we'll stop here today. Thank you very much. Thank you for your sustained interest.